E naught, EA, 1, 2. Okay. So this is the circuit diagram. You have two switches. So here you have two switches and two diodes are there. So this circuit diagram it has both. It can run the machine both in motoring and regenerative modes. Okay. So we will see how it is so. So first, so this is B1. This is B2. Okay. So first we will see that first. First we will see motoring. So in the motoring, what you do is that so switch 1 is turned on. So if the switch 1 is turned on, okay, if the switch 1 is turned on, then what you find out here is that what is the circuit diagram? It becomes if the switch 1 is turned on. So it is EA. This is when the switch is turned on. Okay, when the switch 1 is turned on, so what do you find out? This direction of the current. This is the direction of the current. Okay, this is the direction of the current IA. Okay, so 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 you will find out there is a current flowing from source to the motor and the output voltage is positive. This you have seen. Okay, and when the switch is off, what will happen? When the switch is off, switch 1 is off. If the switch 1 is off, the circuit diagram it becomes now. So this one. So the direction of the current will not change. Okay, it remains same. So then when the switch is off, what is the only option it has left now? The option it has left now is that through diode D2. So D2 will conduct. So your D2 is here. Then we know the switch 1 is on. Okay, so your D2 will conduct. So the direction of the current will be the same, but this time through D2, and that's it. It comes across the part like this. So now you see here, what you need to understand is what is E naught here? E naught is equal to 0. In this case, E naught is equal to EA, but the direction of the current here is that is from source to load. Here also from source to load. So you can say this is first quadrant operation. It is a first quadrant operation. You can simply say this thing, then it is a first quadrant operation. Okay, because in the first quadrant operation, both output voltage and the output current both are positive. That's called motoring control. Now coming to the regenerative control. The same circuit diagram. So this time S2 is on. When S2 is turned on, what is circuit diagram? It becomes EA. When S2 is on, so what do you find out is that EA will be there, but I am sure that EB, RA plus minus because in second quadrant E naught is positive itself. So when S2 is on, what do you find out? What is the closed path you will find out? This is the closed path you will find out. So you will find out this thing that the direction of the current will be like this. This is IA. So E naught is 0 here. When S2 is turned on, E naught is 0. So it makes a closed path like this. Now when S2 is off, When SQ is off, what is the closure path? We will find out. The closure path is something like this. This time, yeah, first I will draw this one. This is LA, this is RA. Okay, so we will find out the direction of the current will remain same. Okay, that is in this direction only. But now this time it takes which path is that? It takes as you turned off, so it will force the diode D1 to conduct through the source. Okay, so here this time E naught, that is equal EA. This is EA. Okay, now this one is D1. So now you see in this case, what you find out is that E naught is positive, E naught is positive, but IA is negative. So E naught is positive in the second quadrant. To the second quadrant. The second quadrant. So first quadrant, second quadrant. So in second quadrant it is behaving as representative braking. So the one simple circuit diagram has both motoring and regenerative braking. So that's the circuit diagram. This is for the separately excited DC motor. Okay. Separately excited DC motor. So then we will go to next one, dynamic braking control. Okay, it's because electrical braking you have some other methods also there. One of them is dynamic braking control. So dynamic braking control. So what do you find out in the dynamic braking control is that, so same separate external DC motor. So the circuit diagram is a little bit different. So in the dynamic braking control, what exactly you do is that you have the resistor, inductor, this EB is there. So this is the motor, RA, LA, EB, okay, RA, LA, EB, okay. So this one is the motor, and you have a switch here. Please recall in the braking case, what do you find out? What do you find out? Okay. So here in the regenerative dynamic braking, you have a resistor here RB. Okay. So then you will find out. Okay. Just recall yourself. This is the direction of IA, because in the braking, the machine behaves as a generator. Then that is, it gives the power back to the source. Okay. So that you know. So the direction of IA is going from motor to the source. But whereas in the dynamic braking control, what is the circuit difference? We will find out is that you have the switch like just like your previous regenerative braking, but in place of the source we have a resistor RB. That's the difference we will find out. First of all, circuit wise, this is the difference. So now we see now what will happen if the switch is on. If the switch is on, what happens if the switch is on? If the switch is on, what is circuit diagram? This is circuit diagram. We will find out. Okay, in the situation is the circuit diagram. So in this case, you know, the current will flow through the switch and the motor. So the switch and the motor, it will flow like this. When the switch is off, please remember when the switch is off. So this is for 0 less than equal to t less than equal to t on. So till t on, the switch is on. So the current will flow through the switch like this. When the switch is off, what will happen now? The current which is there in the inductor will try to continue in the same direction. So it will travel through RB. RB is some external resistance now. So okay, RA, LA, EB. So when it is flowing through RB, the energy stored in the motor will circulate through RB. It will circulate through RB. So now we are interested to calculate what is the energy now. What is the energy? Okay, energy dissipation in RB. E. Energy dissipation in RB. What is the energy dissipation in RB? So how do you find out the energy dissipation in RB? So simple thing that power dissipation in RB, power dissipation in RB multiply with the time. So what is the power dissipation in RB? You can say like this IA square RB. But you multiply with time in the sense it is only during I would like to remind you here that it is only during T off. T off only. That is what is the T off when switch is off. When the switch is off, the switch is off when in this duration. That is T on less than equal to T less than equal to T. So you can take it as capital T. Okay. So during this part, that is from T on to T, that is during switch is off. During this duration, so what is the duration you can say here? T minus T on. T minus T on you can take it as the duration. So that time multiply with the power will be the energy dissipation in the RB. Okay, this is the energy dissipation in the RB. So from this, okay. So I would like to calculate what is the average power dissipation. Power dissipation, average power dissipation in RB. What is the average power dissipation in RB? It is energy divided by the total time period. IA square RB into T minus T on. This is the energy divided by the total time period. Then only you will get the average value. So that is equal IA square into RB. How can I write this? 1 minus T on by T, that is alpha. So this is the average power dissipation in RB. This is the average power dissipation in RB. So then we can write one more thing. What we can write now? This average power dissipation, I will write like this, is equal to IA square into RBE. What is RBE? Is that RBE is equal to RB into 1 minus alpha. You can say RBE can be called as effective resistance. This is called effective resistance. So RBE is the effective resistance. Okay. So this is dynamic braking. What is the difference between dynamic braking and the regenerative braking? In dynamic braking, what you exactly do is that circuit wise, in place of the source, you have a resistor RB. So the entire energy here is dissipating as heat. This is what we find out. So there will be total energy being dissipated as heat. That's one difference. The other difference is that now this is fast compared with the regenerative braking. How I am saying fast is that, okay, you see yourself when you have an extra resistance RB, then this energy, okay, what is the time constant you will find in this case? The time constant is equal to L by R generally. So it becomes LA by RA plus RB. How do you say RA plus RB? Because you see yourself in this case, both RA and RB are in series. So when RA and RB are in series, then total resistance will be RA plus RB. So the time constant, you see the time constant gets reduced. The time constant gets reduced here because denominator is more. Okay, in case of your regenerative braking, you don't have this external resistance. Now in this case, we have external resistance, so the time constant gets reduced. So when the time constant gets reduced, in the sense, this power dissipation will be very fast. So when the power dissipation is very fast, in the sense, the kinetic energy stored in the vehicles, okay, will become zero in less time. So when it becomes zero in less time, it means it comes to halt in less time. So that's called dynamic braking. So that's the difference between dynamic braking and regenerative braking. So in regenerative braking, you have a source, whereas dynamic braking, in place of the source, you have a resistor RB. So because of this resistor RB, the time constant of the circuit will be less. So the power dissipation will happen in less time. It means the speed is more, or the response is fast. The response is fast. Okay, so that thing we have done here mathematically. What is the energy dissipation? What is the average power dissipation using these equations? Okay. So then, what's next is now we will solve a numerical problem now. Okay. So last class itself, I told you that motoring mode. What is the speed torque characteristics? and generating what is the speed characteristic. So combinedly, if you do, then you'll get this. I told you already. This is for increasing alpha. This is for increasing alpha. So this is the speed. This is the torque. Okay. The first quadrant is motoring. I told you already. Whereas second quadrant is regenerative. Okay. So this we have seen already in the previous classes itself, but separately we have seen. Okay. Now this is a combined circuit. Now we solve an numerical problem now here. So what is the numerical problem is that a separately excited DC motor with armature resistance 0.01 ohm, 0.01 ohm with DC supply. Okay, the DC supply is how much? 220 volts, 100 ampere, and 1000 RPM. So is fed with a chopper control for its motoring and braking operations. Okay. So assuming continuous conduction, that's important. So assuming continuous conduction. Assuming continuous conduction, yeah, assuming continuous conduction, calculate first question duty ratio of the chopper at rated torque with speed of 500 rpm for its motoring operation. Second question is that the duty ratio of chopper at rated torque with speed of 500 rpm for its braking operation. So we will always solve the problem from the question itself. What is the question? He is asking the duty ratio of the chopper for two cases. One is motoring operation, the other is braking operation. This is the okay. This is the question it is. Okay, so one by one we'll solve first problem is motoring condition. So in the motoring condition, what is the duty ratio? So what is the duty ratio formula? First of all, formula is where can we find out the duty ratio? That is the first question. Where can we find out the duty ratio? Okay. So then we'll see now. Okay. So where can we find out the duty ratio? So where can we find out the duty ratio? So where it is, we will see that. Okay. So which formula we will have for the duty ratio? So okay. So you see what is the formula is there? This E naught is equal to alpha into EA. Yes, we have this formula. What is EA? EA is the supply voltage of the copper. So EA value is 220 volts. EA is 220 volts. Okay. Then what is E naught? I want to find out what is E naught. So what is E naught? How we find out E naught is that how do you find E naught here? To find out E naught. Okay. So which formula you will use here? So now it is as it is motoring mode. So you recall E naught is equal to EB plus IAR. This is from what about generating braking mode? In the braking condition, you know, conductor. You have seen this thing very well that this is E naught, this is EB. So this is the direction of the current, the braking mode. Then in that case, what do you E naught can be written as EB minus IAR. You see here because you apply KVL, then you will understand here that EB is equal to IARA plus E naught. It means E naught is equal to EB minus IARA. So you got this equation. So now this equation is for the motoring mode. Okay, so everything is same. See both the problems, everything is same except one is motoring condition, the other is braking condition. So I will solve for the motoring condition. Then using this equation, you can solve for the braking condition. That's easier. Okay, then what's next now? What's next is that okay, now you see here. Okay, so E naught. How do you find out E naught? Then okay, to find out E naught, so you have this equation: EB equal to IA plus R for the motoring, whereas EB minus LDR IA array for the breaking. Now in this, what is RA? What is RA? RA value he has given in the problem, I think 0.01. So he has given 0.01. What is IA? IA is the armature current. Now you see in the question it is rated torque. Here also rated torque. So at rated torque, the current is also rated. So what is the rated current? The problem here is not accurate. So I will take IA is equal to 100 ampere. Now what is the only thing it is left now? EB is left. What is EB now? How do you find EB? So EB at which RPM he is asking? 500 RPM. Because why I am mentioning RPM in the sense your back EMF depends upon the speed, that is RPM. Okay, so how do you find out this is that? We'll see the question here once again. So he has given rated values. You please see here. Rated values in supply voltage as well, current has given speed as well. So we will do one thing. We will find out EB at 1000 RPM first. First we will find out EB at 1000 RPM. How do you find out EB at 1000 RPM? What is the formula? What is the formula? Is that supply voltage? Supply voltage. Okay. Supply voltage plus IA, sorry, minus IAR. Minus IARA. This is the same equation. The same equation. So what is supply voltage now? 220 volts. Because everything you will take rated values only. Because he has given rated value. So rated voltage minus rated current 100 ampere into 0.01. So what is the answer here? One. So 219 volts. So at 1000 RPM EB is 219. What is the EB at 500 RPM? What is EB at 500 RPM? How do you find out that? 219 into 500,000. That is equal to 1 by 2. So 219 divided by 2. 109.5 volts. So we got the answer 109.5 volts. So we got EB value. Once we got EB value, what is E naught? E naught is equal to EB 109.5 plus it is 100 because C is 100, it is 0.01. 0.01. So rated value is asking. So 110.5. This is E naught. Okay. So we got E naught here. Then what is alpha then? At the end we will find out alpha. What is alpha? Alpha is equal to E naught by EA. That is equal to 110.5 here. EA is 220 volts. Supply voltage of the chopper or motor. Everything is same in the problem as well. So 110.5 divided by 220. So you got 0.5. So you got 0. This is the degree. So I suggest you to find out that degree ratio in the second problem. What is in the second problem? Second problem you have to do breaking. So EB minus IARA you will do. Then you can easily find out. So here we can find out that that's not a problem at all. So breaking condition, everything you recall what I told you in case of the breaking condition. In case of the breaking condition, what I told you, so current get reversed. So everything you have already from the previous classes. You got all those equations, then substitute here. Then you will get the duty ratio for the breaking case also.